So the topic of today's video will be solution of wave equation and in one dimension, right? And we were doing this topic in our last video. So continuing from that point, right? As I discussed in our last video, the wave equation, its modeling and its solution. Then I will be going to discuss the cases, right, about the boundary conditions or initial conditions for the wave equation, right? So let me recall what was our wave equation, and that was wave equation. Wave equation was 1 over c square u dt is equal to u xx. This is the partial derivative, second order partial derivative of u with respect to t, and this is second order partial derivative of u with respect to x, right? And we'll c was a constant, where c is equal to capital T over rho. T was the tension in the string and rho was the mass per unit length, right? And subject to the conditions. The first is boundary conditions. Boundary conditions, let me call it condition A, right? Boundary conditions, and those were first was u 0 comma t is equal to 0, and the second condition was u L comma t is equal to 0. L was the length of stretched string with its both ends fixed, right, at x equal to 0 and x equal to capital L. Okay, and t is obviously greater than or equal to 0. T stands for time, right? And then initial conditions were first is u x comma 0 is equal to fx, and u del u by del t, I can write it as del u by del t, or you can write it as ut. X comma 0 is equal to gx, right, for x varying between 0 to L, right? So this was our wave equation subject to the boundary and initial conditions, as we discussed in our last video. In this video, I will be going to discuss the solution in much detail as compared to our last one with these conditions, right? If you remember that we started the solution of the form u as a function of x and t, u is equal to capital Xx and capital T of small t. Then I substituted that u here and got two ordinary differential equations by the method of separation of variables. Then I was able to solve them, and I discussed about the nature of this separation constant, that was k, and immediately that came out to be a negative. K is equal to minus p square, and then the solution of this equation with these boundary conditions took the form of something like this. The solution is given by, I am writing the solution directly, u x comma t is equal to a cos px plus b sin px multiplied by c sin px plus d sin px. That was the solution for this wave equation, right? And also we used these two conditions, these two boundary conditions, right? Using these two boundary conditions, if you see here, you want that if you place x is equal to 0, you should get u is equal to 0, right? And you can see that if you put x is equal to 0, this will go to capital A and this will go to 0. Means this cos function is restricting u to get u is equal to 0, right? Which implies that this a should be 0, right? Then I got this. After imposing this condition on my solution, I got this solution, right? Okay. Then on imposing this condition on this solution, I would get p is equal to n pi up over capital L, right? Let me write it directly, as we have already discussed this in our last video, right? I am writing that directly. using condition 1 and 2, the solution is given by after using condition first and condition second, right? That was sine, and the value of p was n pi x over L, that is capital L, and as a function of t I have got c, I think, and cos n pi c t over L plus d sine n pi c t over L, and where n was 1, 2, 3, so on. So this was our solution. We derived this solution using the first and second boundary conditions. This was our solution, refined solution, having lesser number of constants. It has only two constants, c and d, and those will be eliminated if I use this condition number 3 and condition number 4, right? Okay, then you can see that this solution is depending on n, and the value of n starts from 1, 2, 3, and so on, right? And also it can be written as, if I remove this n equal to 1 to 3, then I have to put here a summation starting from n equal to 1 to infinity, right? That is obvious. Okay, then I should use this condition, condition number 3 or 4. Now two cases or three cases arise. The first case is that this gx is equal to 0, right? Means the vibrations are produced by giving the initial displacement. This is the displacement, this is the velocity. If gx becomes 0, then the vibrations will be given by this fx function, means the initial displacement. That should be our first case. And the second case will be when this fx is equal to 0 and this gx is a non-zero, means the vibrations will be given by initial velocity, right? So we'll be discussing these cases one by one. Okay, so let me take case number 1 first. There are, I should write 3 cases, one more case is there, so 3 cases. Case number 1. Case number 1 is that when 0 initial velocity, means this gx is equal to 0, that is gx equal to 0, right? Means vibrations can either be started by pulling the string at one of its points and then releasing it, and that is called vibrations due to initial displacement, right? And this is the case we are going to discuss. Okay, so with 0 initial velocity means the vibrations have been started by pulling and then releasing the string, right, at the moment when t is equal to 0. Let me take fx, some function. Let me take it example 1. Okay, example number 1, right? Suppose this fx is equal to m times, m is a constant, right, m times sine m pi x over capital L, right? M is constant, capital M is a constant, small m is also constant, right? Okay, so this is your fx, right? It means that you have the string like this, and you pick up one of the points of the string and pulled it in a fashion that the shape of the curve takes this function form, means sine function. It may be something like this, a curve of sine, right? Okay, then you released it, and at the time of release, the time t is equal to 0. Okay, so taking fx is equal to this much, I have to impose this condition on this solution, right? This is the solution. I should make a box on it. Fine. Okay, suppose fx is equal to this, and obviously gx is equal to 0, means u of t, using, since condition number 4th is now u t x comma 0 is equal to 0, means the velocity is 0, initial velocity is 0. We are discussing the case with the 0 initial velocity, right? I will impose this condition first. I should say this as a condition number 1 second. That should be u x comma 0 equal to, let me take it, fx, right? And this was our condition number third, right? Third becomes this and fourth becomes this in this case, right? So on this solution, let me name it equation number 1. This is my equation number 1, right? And it is already containing these two conditions, first condition and second conditions, right? Okay, so imposing this fourth condition on this equation number 1, I will be getting, see here, I have to differentiate it with respect to t, right? And then on putting t is equal to 0, I should get u is equal to 0. And if you see that, focus on the t part, do not focus on the x part, because you have to differentiate with respect to t. If you differentiate this with respect to t, then it will become sine and it will become cos, right? And if you put then x is equal to 0, then this term will go to 0 and this will become non-zero, right? I am not going to differentiate it, rather you differentiate in your mind and just try to write it directly. See, okay, then it becomes this multiplied by d times of n pi c by l, and this will become cos, and that will become 1, then it will give me d is equal to 0, right? Okay, since this gives d is equal to 0, you can see it by yourself, verify. This is very easy, right? Or you can think in that way that what should be the value of the coefficient c and d, such that on differentiating it once with respect to t and then putting t is equal to 0, that should give a 0 solution, means u is equal to 0. I want ut is equal to 0, right? And obviously your d should be 0, right? Because this will be converted into cos term, and then putting t is equal to 0, and this will be intact, and to have this whole 0, I have to put d is equal to 0. You can verify it by yourself. Okay, then putting this d is equal to 0 in my solution, therefore first becomes u x comma t equal to, and since d goes to 0, c multiplied by this, I will be getting c sine n pi x over l and cos n pi c t over l, right? And remember that the value of n runs from 1, 2 and 3, so on, right? So either you write n equal to 1, 2, 3 and so on, right? Or if you don't want to write this, just put a summation here, right? And start from n equal to 1 to infinity, and you can remove this, right? And one more thing, since n equal to 1, putting n equal to 1 will give a solution, sine of pi x by l cos pi c t by l. Putting n equal to 2 will give another solution, and their linear combination will be again a solution, as the equation is of linear nature. So I should put an n here, small n, because C1, C2, C3, C4, that will indicate that the solutions are linearly combined. One solution is sine cos term, right? Another solution is again sine cos term, but not just adding them. Their linear combination should be done, and linear combination is done by multiplying all the solutions with the arbitrary constant and then adding them, right? So you have to put Cn here, right? Means this time the constant is also fluctuating. Okay, so this is the refined solution after using this condition number 4, the 0 condition. Now I am left with this condition, this one, ux0 is equal to this thing. I have to use this condition here, and okay, using condition number 3, right, means the displacement function. Okay, plugging this here, I will be getting summation n equal to 1 to infinity Cn sine n pi x over L, and putting t is equal to 0 here, that will give me 1, right, is equal to fx. And what is your fx? Your fx is this one, m times sine m pi x over L. Fine, right. Now you have to do comparison, right, because luckily this time both terms are containing sine terms, then you can compare them. And then first you allow yourself to put this n equal to 1, 2 and 3 and so on, then you will be comparing these both two sides, right? If you put n equal to 1, you will be getting something like this: C1 sine pi x over L. The second term will be C2 sine 2 pi x over L, and so on, and plus Cm, m will be there obviously, Cm and sine m pi x over L, and this series will go on to infinity, right? And this m times sine m pi x over L. Now I have to do comparison, right? And you can compare only this term. See this angle sine m pi x upon L, right? Okay. This implies that Cm is equal to capital M and right. Okay, fine. This implies that on comparison, C1 equal to C2 equal to all C's are 0, m minus 1 equal to C, m plus 1 equal to dash dash, they all are 0, right? Except this Cm, and Cm equal to capital M, right? Fine. Then this will give me, in my last solution, this was my solution, is solution. Let me call it equation number 2. Every time I will be getting a refined solution, I will name it some new equation, right? And then putting this in equation number 2, equation 2, right? I will be getting u x comma t is equal to, right? Since all the infinite series terms, of all the infinite terms, only one term is live, that is Cm equal to m. I will put Cm equal to capital M here, capital M, and sine, and obviously I should write it as n is equal to m or Cm equal to m or okay, fine, sine m pi x over L and cos m pi ct over L, right? Fine. Or I can write it as n here, n, and now this is fine. Cn equal to m, Cn equal to m, and n equal to small m. Okay, now it is fine, right? So this is the required solution, is a required solution. Okay. Now see this example, you can see that I was able to do comparison to both sides, but every time it is not the case. Sometimes you have a quadratic or a cubic function here. In that case, you cannot compare these two sides. Comparison can only be done if the same nature of function is present, sine sine or cos cos, right? Had I got here some quadratic or cubic function or exponential function, I cannot compare the two sides, right? So this comparison is feasible if and only if the terms on both of the sides are comparable, or you can say that this comes from fx. This is fx. Fx was of nature of sine or cos. But what happens if fx is not of the nature of sine or cos, right? Then I will be taking another case, another example, example number 2, where I will change my fx, right? Example number 2, under this 0 initial velocity. Suppose you take third condition changed, u x comma 0 equal to, let me take as a triangular wave function, and that is x, and here I should write L minus x, and this is for 0 to L by 2, and this is for L by 2 to L, right? Fine. And this is a triangular wave function. It indicates that if you draw the graph for this, that will be of the form, this is your x, this is ux, means at time is equal to 0, the string is stretched between these 2 points. This is 0, x equal to 0, and this is your x equal to L, right? L comma 0 will be the coordinate, and this will be 0 comma 0, right? Initially the string was at this point, at this over the x-axis, then To start the oscillations or to start the vibrations, you pick up the middle point of this string here. This is L/2, and you just hold the string at its middle point and you pull it upwards, right? This way, the string takes this form. Okay. Then this point will be, I think, L/2, comma. What is y coordinate? L/2. Yeah, L/2, comma L/2. Right. Okay. And at this point, when you pull the middle point of the string, you just release it. You just release this string because it is already a stretched string. You release it, and it will start oscillating. Right? It will produce vibrations in it. Fine. So it indicates the initial position at t is equal to 0. This is the position of the string at t is equal to 0, right? And you can see that the equation of this line will comes out to be, I think, y is equal to x or u is equal to x, u equal to x, right? And the equation of this line will come out to be u is equal to L minus x. Fine. You can find these equations of a straight line, okay, by using the slope formula. Fine. So we have this function this time, and obviously this fourth condition will remain same. This one will be same. Fourth is u t x comma 0 equal to 0, right? This is same. So using my fourth condition first before this non-zero function, and that will give me the same thing, d is equal to 0, gives d equal to 0. You should verify by yourself. Fine. Then I will be having first becomes u x comma t equal to summation n equal to 1 to infinity, and let me put n here, sine n pi x over L and cos n pi c t over L, right? So this is my solution. Let me call it again, this is equation number second. Fine. So I will repeat that equation. Equation number second is same. Fine. Now difference is here in this step third, because I have changed this ux function. Now using third, right? And this is my third. Putting t is equal to 0 here, that will produce a 1 here, right? And that will be equal to this ux fx. Let me call it fx. Okay. And this is my fx equal to f of x. Okay, fine. Then that will produce n equal to 0 here. Fine. That will produce fx equal to that much value. Fine. Summation n equal to 1 to infinity and cn sine n pi x upon L. So this will be the equation after plugging this t is equal to 0 here in equation number 2, right? And this is the condition. See, this time the difference between these two equations, at this moment I was able to compare the sine function both sides, but here you cannot compare the sine with this fx and see the nature of the fx. This is not of sine or cos form. This is some linear equation, right? And you cannot compare them. Rather, you have to use the famous Fourier series expansion. If you watch it closely, you can see that this fx, right? This fx has a series expansion, a sine series expansion. All terms are of sine terms, and that is called Fourier sine expansion, Fourier half range sine expansion. You have to use Fourier sine series formula here to find this coefficient. We have formula for Fourier coefficient. You must have read in your previous semester course, first semester, second semester, right? So I am applying that formula using Fourier sine series. You can see that the right hand side is a series of sine, Fourier sine series, and this coefficient Cn should be equal to, the formula is 2 over L, right? Integration 0 to capital L, right? And this fx multiplied by sine n pi x over L dx, right? And I am putting a star on this formula you have to remember this formula or recall this formula from your last semester course Fourier series, right? Then I will be going to integrate that. Okay, I have to rub this first. Okay, so plug in the value of fx from here and see the fx is defined for two different domains. One is from 0 to L by 2 and L by 2 to L, right? So I have to split this integral in two separate integrals, and that will give me implies Cn equal to 2 by L, right? And first will be 0 to L by 2, and the function is x times sine n pi x over capital L dx, plus the second integral will be L by 2 to L, and the function is L minus x multiplied by sine n pi x over L dx, right? Now you have to apply the integral by parts rule or shortcut formula, and that will give me 2 by L x, and integration of this will be minus cos n pi x over L n pi x over L over n pi upon L, right? And this is should be inside bracket. Then minus differentiation of this term will be 1, and integration of this will be minus sine n pi x over L over n square pi square over L square, right? And then it will become 0. Fine. Limits are 0 to L by 2, and similarly applying the same formula for this, let me put 2 by L here, 2 by L, okay, and this will give me L minus x, and here the same minus cos n pi x over L over n pi over L okay, and then minus the differentiation of this will be minus 1, and then minus sine n pi x over L over n square pi square over L square. Fine, and limits are from L by 2 to L. Now it all remains to plug in these limits. Okay, so plugging this L by 2 here, I will be getting 2 by L and L by 2, right? L by 2, and this L goes there. That will become ultimately L square upon 2 n pi, and then putting L by 2 here, okay, that will be cos n pi by 2, and cos n pi by 2 is 0, so no need to write this term, that will go to 0, right? And similarly putting L by 2 here, that will produce n pi by 2, sin n pi by 2, so it will become sin n pi by 2, and sine of n pi by 2, okay, that may vary, sin n pi by 2, 1, 2, 3, right? Sin n pi by 2, right? And this will go up L square over L square over n square pi square. Fine, and then putting 0 will give 0, and this will be also 0. So this is my first bracket. Okay, then similarly solving for second, putting L here, that will produce 0, putting L here, that will be sin n pi, and sin n pi is 0, so upper limit will produce 0 terms, and putting L by 2 here, L by 2 will produce cos of n pi by 2, and that is again cos n pi by 2. No, cos n pi by 2 is not 0 every time. Cos n pi by 2 may or may not be 0. That will depend on even and odd values of n. I think I should retain one of the terms from here, right? Let me rewrite it again. Fine. So putting L pi by 2 here, L pi by 2, that will produce a term of this type, minus L square upon 2n pi, right? Now it is fine. L by 2, it is fine now. And here I will have cos L by 2 cos n pi by 2. Actually this is not 0 every time. It will be 0 if n is an odd number, and if it is n is an even number, it is plus minus 1. Okay, fine. Then but this term will go to 0 because sin n pi is always 0 for all values of n. Okay, then putting the lower limit, that will produce 0 here and 0 here, that is fine. Okay, okay, 0, right, fine. And similarly for this bracket, this one, again this is not 0, sin n pi by 2 plus L square over n square pi square sin n pi by 2. Now it is correct. Okay, now for this term, L goes to 0, this will go to 0, sin n pi 0, then putting L by 2 here, L by 2 will be sin, okay, that will be retained, and that will produce 2 by L, and that will give me L by 2 and L square over 2 n pi, fine, and this will give me minus cos n pi by 2, right, fine, and we have one more minus here, so that it will become plus, fine. Okay, and similarly putting L by 2 here will produce, okay, L by 2, okay, that will produce minus minus plus minus, and then it will become plus L square over n square pi square sin n pi by 2, if I am not wrong, right, and I will recheck my calculation again. 0 will produce definitely 0, L will produce 0 everything, and L by 2 will, this term will be there, L by 2, okay, cos L by 2, fine, and this is L by 2 sin n by 2. No, it is fine, I think it is fine, right. Now I should simplify them. I think these two terms should be cancelled, right, fine, this will be cancelled and this will be added up to give twice of this and twice of this, that will become 4 times, and over L, I think n square pi square, and I have L square in the numerator also, then it will produce L, and that will give me sin n pi by 2. Now it is fine. Okay, perfect. This is the value of this Fourier coefficient Cn. Okay, then plugging this Cn in my last solution, where is that, equation number 2, that will be my solution. Therefore equation number 2 will give me u x comma t equal to, and note that this n runs from n equal to 1, 2, 3 and so on, right. Okay, then I will plug this Cn here in equation number 2, and that will produce summation n equal to 1 to infinity, this Fourier coefficient 4L over n square pi square sin n pi by 2, right, and then sin n pi x over L and cos n pi ct over L. This is the solution, It is not containing any arbitrary constant now, right, and you can see that for n equal to 1, that will be sin 90 will become 1, and n equal to 2 means for even values of n, all the terms will be 0, means if we put n equal to 2, we will get sin pi, that will be 0, if we put n equal to 4, that will sin 2 pi 0. For even values of n, the solution will be 0, right. So this is the final solution, fine, and let me take my case number 2, when the vibrations are started by giving the initial velocity this time, right. So I will rub this. Okay, so case 2, case 2, and case 2 is the zero displacement, zero initial displacement, zero initial displacement, that is fx is equal to 0, right? Fx is equal to 0. Okay, so I'm taking example for this, example number 1, and let me take fx is equal to 0. Fine. A third condition is u x comma 0 is equal to 0. Fx is 0 now. And fourth condition, u t x comma 0, let me take it as b sine cube pi x over L. B is a constant, right? So this time I have taken zero initial displacement opposite to case number 1 and some non-zero initial velocity. So vibrations will be started by flicking the string, not pulling it and releasing it, just flicking the string at one of its points, right? Okay. And okay, solution on equation number 1, as we had here, equation number 1, okay, I'm putting this condition using condition number 3, that is u x comma 0 equal to 0 gives, I'm writing that equation directly, but because I don't have that equation here, but remember that equation that was containing sine function as a function of x, and inside we had cos and sine functions of t, right? And you want that if you plug in t is equal to 0 in that equation number 1, then that should produce a 0 solution. It indicates that the t function, this is for t, the t function should be of sine function, because putting t is equal to 0 in sine will give me 0, right? It indicates that cos function will not appear there, right? Then gives u x comma t, and if I remember my constant was, I think, c and d, my constant was d before sine, right? And that will produce sine n pi x over L and sine n pi c t over L, right? And also these, here we have this n, so I should write it as dn, as I said earlier that this is a solution for all different values of n equal to 1, 2, 3 and so on, so all will be solutions, and the linear combination is again a solution. That's why I have to write dn here, right? And then I will put a summation here, summation. N equal to 1 to infinity. This is my u x comma t equal to this much. Fine. And okay, now third condition is imposed on my solution, and now I will be going to impose my fourth and last condition on this solution, but for that I have to obtain this del u by del t, right? Now del u over del t x comma t will give me, differentiating it with respect to small t, will produce summation n equal to 1 to infinity dn times n pi c over L, okay, sine n pi x over capital L and sine n pi c t over capital L. This is the result after differentiating partially with respect to t. Now, and what is the nature of t? You can see here ut is this thing. I will at x at t is equal to 0 using condition number 4th, putting t is equal to 0 here, and that will produce this, sorry, that will become cos, sine becomes cos. Okay, fine. This will become 1, and I will be having b sine cube pi x over L equal to summation n equal to 1 to infinity and dn n pi c over L, let me put a bracket here, and sine n pi x over capital L, right? Now you can see that the right hand side is containing the sine terms and the left hand side is luckily sine, not sine but sine cube, but that can be converted into sine functions, if you don't want to use that Fourier series integral, because that is too much complicated to integrate them and putting the limits correctly, right? That is complicated as compared to the comparison on both sides. So I will be rather changing this sine cube theta in terms of sine 3 theta angle, right? So using that formula, and that formula is, I have to add that formula here. That formula is sine 3 theta equal to 3 sine theta minus 4 sine cube theta, and from this formula sine cube theta will become by 4 here, and sine 3 theta minus 3 sine theta, right? I will be using this formula in order to do comparison on both sides. Fine. So this becomes b, fine, and that will give me b by 4, right? Sine 3 times of theta, this is my theta, 3 times pi x over L, and then I have minus, then again 3b by 4, fine, and sine of theta pi x over L, right? And now I don't need this formula, okay. And the right hand side, and since the left hand side is as a sum of two sine functions, so I have to put n equal to 1, 2, 3 and so on. So I will see here n equal to 3 and n equal to 1, and the rest of the terms will go to 0, right? Or you can write it as this way, d1 pi c over L sine pi x over L, and then putting d2 pi c over L and sine 2 pi x over L, and in the third term d3 pi c over L sine 3 pi x over L, and rest of the terms you don't need to write all these terms, you just see your terms, means you can compare these two terms, right, and this one, and the rest of the coefficients will go to 0. On comparison, this will give me will that d1, that will give me this coefficient equal to this coefficient, and that will give me d1 equal to that will give me bl over 4 pi c, right, for n equal to 1, and d3 equal to see here bl upon 4, where is that, 4 pi c, 4 pi c, d3 both are same, sorry, this is minus 3 by 4, so it should be minus 3b, and 4 is already there, no? Right, fine, so 3 will be there extra, okay. So these are the value of d1 and d3, and rest of the coefficients all 0, right? So plugging this d1 and d3 here in my last solution, where is my last solution? I think this was my last solution, yes. Let me call it equation number 3, fine. Therefore, third becomes my final solution, and uxt equal to, and this is summation, but you know that only two terms will be there, d1 and d3, so all terms will be 0, so no need to write summation now. You should write the first and the third term, at the d1, and d1 is for bl over 4 pi c, and that's multiplied by this sine of n equal to, remember that this is d1, right, d1, so n should be replaced by 1, okay, sine pi x over L and sine pi c t over L. This is for the first coefficient d1, right, and now comes the d3, then put n equal to 3 here, and that will give me plus the value of d3, and that will become minus, I should put minus here, minus 3bl over 4 pi c, and sine n equal to 3, n 3 pi x over L, and then sine 3 pi ct over L is the final solution, right? So this is the answer. Okay, right? So we have discussed the two cases, one for zero initial velocity and this one for zero initial displacement, and let me discuss the last case with non-zero initial velocity and non-zero initial displacement. This is my case number 3rd. Case 3. Case 3 is non-zero initial displacement and velocity, right? Means displacement is also non-zero and velocity is also non-zero, and thinking of that guitar string, right? If you want to give the non-zero displacement and non-zero velocity, that can only be done by picking one of the points of the strings. If you pick the middle point and you pull it, right, and you just not release it like as we did earlier, right? That because that will produce a zero velocity case, right? You pick up one of the point of the string and you pull it, and rather than releasing it, you just flick it at this point, and that will produce this case number 3. Means you have some non-zero displacement and you have some non-zero velocity. Means picking up the middle point of the string and then flicking it means giving the velocity as well as initial displacement, right? So in that case, my problem will be, the conditions will be u3 ux comma 0 is equal to fx, that is not equal to 0, and fourth condition will be ut x comma 0, that is gx, that is also not equal to 0, right? For okay, fine. So this will be the case, and to find the solution for this case, what we need the solution is given by u x comma t equal to u f x comma t plus u g x comma t. This will be the solution. And what is this uf and what is this ug? Where uf x comma t is the solution obtained by taking gx is equal to 0, that is 0 initial velocity, and ug xt is the solution obtained by taking fx equal to 0, that is 0 initial displacement, right? So this case number 3 for non-zero initial displacement and non-zero initial velocity, that is actually the combination of our last two cases, right? Means you have to find the solution by splitting the problem into two parts, right? First part you have to take gx is equal to 0, and for the second part you have to take fx is equal to 0. You will find the solutions for these two parts separately, and then you will add them. That will be the complete solution. So this is the idea, right? Means case number 1 and case number 2 will be the foundation to understand this case number 3, right? And what is this uf? Means the solution obtained by taking gx is equal to 0, and that was our case number 1, right? And what is this ug? This ug is a solution obtained by taking fx is equal to 0, and I think that was the case for our case number 2, right? And I'm not writing an example for that because that is a direct result. If I make some example with some non-zero fx and non-zero gx, you have to split that problem into two parts, and then you will merge them, means you will add them, and you will get the full solution, right? So that's it for this video. Next video we'll be doing some more on wave equation or heat equation. For this video, thanks.